all of the different properties today. Mechanical properties can be enhanced significantly by tailoring the design of composite materials. And many people don't realize that electrical properties are also customized with combinations of materials. As we will see, combinations of fillers can really impact electrical properties. And physical properties are often the first thing that need to be considered. For example, if a part is exposed to extreme temperatures, that has to be the number one consideration just before you even get started. So let's talk about mechanical properties. Mechanical properties are highly influenced by the fiber. Tensile is mostly driven by fiber, while compressive and shear are primarily affected by the matrix. Flex, since it's a combination of tensile and compressive, can be affected by both fiber and matrix. You can get more detail on these properties in the handouts that are available to all attendees today. As I mentioned previously, many people will simply measure fiber content by weight. If you are working with composites, it's important to consider fiber content by volume. There are simple rule of mixture formulas that can be used to estimate tensile strength if volume fractions are used. The equation above illustrates how easy it is to estimate tensile strength in a composite using volume fractions. Obviously, as fiber content goes up, fiber volume goes up, so will mechanical properties. Once fiber volume gets to a point where resin can't wet out the fiber, composite properties will start to go down. And they go down quickly because flaws are introduced into the composite. That threshold may vary by process and fiber type. Typically, 60 to 75% fiber volume is an area where the upper threshold of fiber volume is found. What happens if we change from E-glass to T700 carbon fiber? Using rule of mixtures, we can easily calculate the theoretical tensile strength for each situation. Assuming we have the same fiber volume for each type, we don't have any other influence from fiber orientation, from flaws, or fiber matrix adhesion, we can see that tensile strength should increase over 40% just by switching the fiber from E-glass to T700 carbon fiber. Fiber orientation also has a correlation to nearly all mechanical properties. When designing, cost needs to be considered because optimizing fiber orientation usually comes at higher cost. For example, random fiber mat is very inexpensive, but quasi-isotropic fabrics that provide fiber placed in 0, 90, plus 45, minus 45 orientations are very expensive, but the properties obtained by using them are nearly isotropic. Hence, the name quasi-isotropic. Based on this curve, we would expect that the tensile properties transverse to the 0 fiber orientation would only be around 15% of the properties found in the 0 direction. Random bidirectional and quasi-isotropic orientations should also provide about half to 2/3 of the tensile properties found in the 0 orientation. How about electrical? Composites can be used to customize electrical properties also. Typical electrical properties start with the resin or the polymer characteristics. Those characteristics can be enhanced with additives and fillers. Just like the mechanical properties, flaws and voids are not good for electrical properties either. For example, a good, smooth, flawless surface can improve track and arc resistance. A surface with flaws or fibers showing can provide an arc or tracking path. Thermal performance in many cases is the first thing we have to consider. The resin or polymer used is the primary consideration for thermal performance. Everything after that is an enhancement to that primary polymer's performance, or it could be detrimental to that polymer's performance in thermal performance. Flame resistance can also be achieved chemically or naturally with fillers. Fillers that release water or quench the fire by consuming the oxygen around the fire. Some resins are more stable and inherently more flame resistant. Adding filler or other additives only improves flame resistance if it can quench the fire. Water absorption is a function of how easily water attaches to or leaches into the composite. If the resin is chemically receptive to water molecules, water absorption will be higher. If the composite is microporous, water will find home in those pores.